when I think about Julian, I kind of think that, I think this lecture is for our department kind of like the Lincoln Memorial is for Washington, D.C., in that Julian was not our founding father, but he's arguably our greatest statesman. He's really a tremendously interesting guy, and I'm really glad to be affiliated with a department where he was a big leader. And if you want to find out how interesting he was, I encourage you to go to the Ezra Magazine website and find this very, very humorous article about Julian's activities, and you'll just be surprised what a guy he was, right? So Dave Allen from University of Texas is our speaker and is a special old friend of mine. He's the holder of the Melvin H. Gertz Regents Chair in Chemical Engineering. He got his bachelor's degree here at Cornell University in 1979, then went to Caltech the same year, same term that I went. So we were classmates together, and we're both from Pittsburgh, so we quickly became friends and made a habit of studying together and playing together, and we've had a number of great adventures together at that time. He was a varsity athlete here on the cross-country team, and with so much to do in chemical engineering at Cornell, to survive as a varsity athlete is a special accomplishment. After graduate school, he finished in 1983 his PhD working with George Gavalis on conversion of coal to liquid fuels, and then took a faculty job at UCLA. Was there for 12 years. Rose through the ranks and became department chair, and then moved on to University of Texas. Has been there just over 20 years. Both at UCLA and at Texas, he's worked on a broad range of problems having to do with energy engineering, sustainability, and air quality. And his CV, if you look at it carefully, it shows an unusually noteworthy contributions to public service over his career. And we heard about this in his talk yesterday when he was telling us about leading a monstrous effort to measure emissions from oil and gas operations in Texas that led to significant changes in regulations that have profoundly impacted the climate, or the air quality, particularly in the Houston area. In his business of academia, we kind of hand out awards like Halloween candy, and when you're as good as he is, you have a list that's so long, we don't have time to read it. But I would pick out a few that I particularly am impressed by, because they come from our professional organization, the American Institute of Chemical Engineers, and I've been on panels that give these awards. And it's done with a very thoughtful process. These are not easy to win, and winning one of these means that you are really highly respected by your peers. And Dave has won 3 of them. He got the Lawrence Cecil Award in 2000 for outstanding chemical engineering contribution achievement in the preservation or improvement of the environment. A Research Excellence Award from the Sustainable Engineering Forum of the AICHE for basic or applied research results relative to the sustainability of products, processes, or the environment. And then a Warren K. Lewis Award for chemical engineering education in 2011, which recognizes distinguished and continuing contributions to chemical engineering education. And I think what we'll hear today is something that's closely related to that. So my son is a junior high schooler, and we've been very actively trying to figure out the best high school circumstance for us. And one of the things you learn is that all the good high schools now want to have a robotics laboratory and a 3D printer, right? And this is engineering education coming into high schools. And I think Dave's going to tell us today how to think about this and how to integrate it with our engineering education in college. So
Thanks, Brad.
You're welcome.
Okay, so now today I'm going to talk about something very different from yesterday, and talk really about an activity that I've been involved with for the last 8 years that took me somewhat by surprise, and that's the extensive engineering education that's currently occurring in American high schools. I'm going to go through a variety of parts in this talk. I'm first just going to talk a little bit about how personally I got engaged in this and what motivated me to become involved and spend a lot of time over the last 8 years on high school engineering. I'll then make the arguments that led our Cockrell School of Engineering at the University of Texas at Austin to incorporate this in a big way in what we're doing. I'll then describe to you a little bit about what this curriculum is that we developed, how we work with high school teachers, what's next, and then perhaps suggest the many questions this raises for the profession of engineering in the United States. So let me begin just with these personal reflections and how I got involved in this. I had no idea what high school engineering education was about 8 years ago, even having had a couple of kids go through high school. But then at that point in time, the state of Texas changed high school graduation requirements. It had been that to graduate from high school in Texas, you had to have 3 years of science: biology, chemistry, physics. And state of Texas changed that to requiring also a 4th year of science. That 4th year of science could be taken from a relatively short list of the common group of suspects. So advanced chemistry, advanced physics, environmental science, a number of other things that you probably encountered in your high school experience if you're a graduate student. But something that was new was a course in engineering. Now, here at Cornell, the undergraduate population is drawn from all over the world. At Texas, 95% of our undergraduates come from the state of Texas. And so suddenly now, if a large fraction of our students are going to be learning engineering in high school at the University of Texas, we want to know, well, what's in that? And who's going to teach it? And as I learned more and more about engineering education in high schools, I became more and more convinced that the future of engineering in high schools in the United States is going to be very closely tied to the future of the profession of engineering in the United States. So ask a chemist, why did you become a chemist? And you'll get most commonly one of two answers. Either I knew someone who was a chemist, or I had an inspirational teacher in high school. And in engineering, we've always had the I knew someone who was an engineer, but we really have never had the inspiration in high school. Further now, the first introduction to engineering as a profession will be in high school. And opinions about the profession, the students who will be attracted to the profession, are going to be profoundly influenced by what happens in high school. So all of those things motivated me to get involved with this. I don't know why this is doing this. So why did a top-tier school of engineering get involved in this in what's amounted to a pretty big way? Well, the statistic that I like to cite, that now is somewhat dated, but it's the only one that I can really provide a citation for, is how many students are doing engineering in high school. And by this I mean graduating with formal credits in engineering when they graduate from high school. Not a robotics club, not any sorts of electives, but a year-long experience or more in high school. And I believe this number underestimates the truth by at least a factor of 2 currently. But you can see that we're already above the number of students graduating with BS in engineering in the United States. There are more students graduating from high school with credits in engineering than there are college students graduating from engineering programs. So going forward, our undergraduates are going to come in with some sort of experience that's based on what happens in high schools. And yet, very little is known about effective engineering instruction in high schools at the secondary level, both the curriculum and the nature of the instruction. So, very few curricula out there. And the problems are that really that we don't have available, affordable high school engineering curriculums accessible to a large number of students. Further, you ask yourself, who's going to teach the courses? There's a lack of availability of trained teachers who could teach an engineering course. Just anecdotally, I will tell you that the hardest thing about teaching, preparing a teacher to deliver engineering in high school is the mindset that there's never a single answer to an engineering problem. In math, 2 + 2 is always 4. right? In engineering, there are multiple solutions to a problem, and getting a teacher prepared to accept that is a challenge. So we've been working for the last 8 years then on our attempt to try and address this problem, and we've developed a curriculum called Engineer Your World. It's been nationally vetted. We try to keep it low cost. I can talk about costs if you have questions at the end. That is a year-long high school engineering course. And we've made a strong commitment to teacher development and support. So our curriculum then, which is a central part of our program, is this Engineer Your World year-long curriculum. We've also developed degree programs. So we've got, at places that have colleges of education, many students coming through who are attempting to prepare themselves for a career in K through 12 education. We have two types of students that we encounter. One is typically students who are pursuing a bachelor's degree, again, trying to get to a career in K through 12 education, particularly teaching in STEM, science, technology, engineering, and mathematics. But if they're going to teach engineering, how are you going to prepare them? Our colleagues in chemistry, so my chemistry department at the University of Texas, has courses explicitly for students who are on the track to prepare to be high school teachers. Same thing in physics. Identify for me more than one course in the United States that is for engineering, taught by engineers, that's preparing to deliver a training for university students who are preparing to go into the K through 12 environment. Simply don't exist. Then we have graduate degrees for current teachers, practitioners, who are coming back to get an MA in education and want to specialize in engineering education. So you've got to support teachers in that way. And then, as I'll mention, all of this work was supported by the National Science Foundation. And so as we've been developing this program, we've been continuing to do research on it, trying to continually improve it, and of course doing independent evaluations of it. So these are elements of our program. How did we grow it? We began first offering the curriculum back in the 2011-2012 school year. We started small. We went to 7 schools in Central Texas. Local schools, we knew the schools well, knew the teachers well. We had a first draft of the curriculum, and we offered it in those schools and got an awful lot of feedback. And we had about 200 students involved in that activity. The next year we thought, well, could we support this in regions outside of schools that we can drive to if there's a problem? Can we support it remotely? And so we went to about 25 schools in 8 states and bumped up the numbers of students. We discovered we could support teachers remotely. We then thought, well, is there a big market for this? And let's try and market this a bit more aggressively. And we tripled the number the next year. We then decided that this might grow quite a bit larger and that we'd better think about a way to sustain this after the National Science Foundation support went away. So we began a business model that involved a licensing fee for the course. And we lost some schools when things weren't free anymore entirely, but we gained lots more. And we held about even in the number of schools that we had. This year we're in about 115 schools. Next year at least 180. And we've done all this with relatively little in the way of formal marketing. So we're in an aggressive growth stage. We think that there's a lot of potential for large numbers of high schools. Give you a sense of where these are. You see on the left where our schools were. That first year we were thinking about a national distribution. And then on the right, this academic year's schools. So we have a lot in Texas and then clustered in various places. Your eye probably went here. And yes, we are doing things in upstate New York, as I'll talk about in a little bit. When you think about integrating things into high schools, one of the things to recognize is that unlike chemical engineering, where curricula, at least in the United States, are pretty uniform throughout the United States, and accrediting agencies are national in scope, in K through 12 education, there's a lot of differentiation between states. And so we need to make sure that that our curriculum satisfies as many different state standards as possible. And this is just a short listing of some of those. I'm not going to dwell on this, but we're cognizant of this as a challenge. We want to design this course so that it addresses diverse audiences. And so this shows you a little bit of data. Let's first just look at the gender distribution of the students in the course. So on the far right in each of these groups of bars is the percentage in the U.S. national population of each of these groups. On the far left, the light gray bar is the percentage in BS degree recipients in engineering in the United States. And then you see our previous 3 years of participants among high school students in our classes. So we're doing somewhat better in attracting women into a high school engineering course than the field does in graduating women as BS engineers. We are also majority minority in our overall population, particularly with high Hispanic populations. So we attract students who perhaps haven't been well attracted yet to university-based engineering curricula. So this is growing fast. Think of it like a startup. We've got a very growing market. Let's talk a little bit about the content of the course. So what's in it? What are we trying to deliver to students? When Texas established its requirements for this 4th year of science, the prescribed prerequisites in mathematics were Algebra 2. So this is not calculus-based, but it's algebra-based. We presume that our students have retained some of their physics. Maybe not all of it, but have retained some of their physics. So with that as prerequisite, what's in the Engineer Your World curriculum? The first thing we want to do is make sure that these are relatively authentic engineering practices, as authentic as we can make them. We also want to make sure that this is project-based instruction, that students are building things, they're testing things, they're having hands-on activities. And that the teacher, rather than standing up here and lecturing as I'm doing, will guide the students through explorations. The model is that the students should be discovering these engineering principles as they're going through the curriculum. So we want to teach them engineering skills, which are also commonly called 21st century skills. We want to teach them innovation, show them the creativity of the engineering discipline, teach them about critical thinking and problem solving, how to work in teams, how to communicate, how to collaborate. And then we want to give them a broad exposure to many different engineering fields. So those are guiding principles. And I'll describe it a little bit to you here. I apologize, this didn't turn out so well. And you can't see the small little shaker table that exists. So it's a computer-controlled shaker table, all right, that can oscillate at variable frequencies only in one dimension. Attached, and we can control that from a PC. Attached to that, we'll place accelerometers. We put an accelerometer down here on the shaker table so that we know what the actual driving force for the building movement is. And then we'll put another accelerometer at various points in the building, and we'll record the accelerations. And the goal of the design exercise is to design a building that will be safe under both no roof load conditions and presuming you're in an area that, for example, might have snow, under roof load conditions. And the students then collect a lot of data with different sorts of bracing structures. They pay a penalty for every little bit of bracing that they put in. So they're trying to minimize cost. At the same time, they're trying to stay within constraints of maximum acceleration. And they go through multiple iterations of this design process, learning how to collect a lot of experimental data, use that experimental data, refine their designs, and move on. We can also teach them some basic principles like resonance. And I'm going to just play a part of this. So you can demonstrate this with our same shaker table. You'll see the shaker table here again. Didn't start, yep. So you see the shaker table at the bottom, and it's going at a particular frequency. Shaker table is designed to move at frequencies that are pretty typical of earthquakes. And you can measure the displacement of this, and so we're trying to get the students to think about, well, what are the accelerations, what are the forces? But if we move along a little bit further, we can see that there are particularly catastrophic things that you want to avoid. Like if we have the mass a little too high, you may very well develop a resonance that will give you potentially catastrophic motion. And we have lots of designs that the students come up with that will simply break apart because they do happen to hit the resonant frequency. So lots of basic principles that they can learn about through these relatively simple examples. Next is to deal with reverse engineering. So take an existing design, in this case a mechanical flashlight that's powered by hand, and improve the design in various ways and test function on it. So how do you take an existing design, make it better? We try to keep the students away from electricity. But nevertheless, we want to teach them about electrical engineering. And so we have them try to program their favorite song through developing some basic coding and to generate a circuit that will play their favorite song. And that will introduce them to some basic concepts of software and electrical engineering. Finally, the last challenge in the course was developed by a NASA engineer who came and spent a year with us. And the problem that she really wanted to address was getting systems integration into all levels of engineering education. And so the goal here is to develop a system that will lift a payload up to a certain altitude, will then release that payload. That payload will then do a controlled descent. While it's doing the controlled descent, it will need to take pictures of an object, a target, on the ground at various elevations. That's the design problem. And so the students are broken into teams. One team designs the lift. The other designs the descent mechanism. A third designs the camera and image acquisition system. And then they've all got to come together and make sure that their system as a whole works properly. So not just doing the individual parts, but breaking this into subsystems and then having the whole system work together effectively. So that's broadly what's in the course. So this is what the students experience. How do you get teachers ready to do this? So every summer we start with bringing in teachers for 2 weeks of professional development. So far we've done that exclusively in Austin. We're now, hopefully next year, going to be doing that at other locations around the country. But we have the teachers come in and very rapidly experience what their students will experience in doing the course. And in addition then, throughout the year, we're essentially continually on call for the teachers. So if they have any questions at all as they're implementing our course, they call us up and get support from us. We give them monthly video conferences. There's an emerging professional network of teachers in some 20 different states. We're having some of those teachers trained as mentors for their peers. And then again, we're continually on call. So that's where we are right now. We've got this one-year course. It's grown really rapidly. It's been a lot of fun. What's next? Most important, I think, and in some ways this is the thing that currently scares me the most, is how do you demonstrate that this is really equivalent to what a student would experience at a freshman level engineering course at a top tier engineering school in the United States. That's the argument we make. That if you went to Colorado or Michigan or MIT or any other place that has a really extensive freshman engineering design program, you would see this same level of course. How do we demonstrate that? There is currently no AP in engineering. You can't demonstrate it in the way you demonstrate college level competency for chemistry or physics. How do you do it? And so what we're doing right now is we've created a 3-unit course at the University of Texas at Austin. The students take the assignments that they've completed in their high school classroom, write them up according to the standards that we at UT Austin define, maybe different than their high school teacher. We'll define how they write those up. They submit them, and that becomes the material that they use to satisfy the requirements of this 3-unit course. So we're trying this out. We're trying it out this semester for the first time. We took 4 of our 180 schools, and we have something like 22 students currently in the course. I'm teaching this course, and it looks like all 22 students will finish. That 22 students represents about 20% of the students in those 4 schools who are enrolled in the curriculum. And what makes me nervous about this is next year we've committed to offer this opportunity to all 180 schools in our program. And if all 8,000 students are offered the opportunity and 20% want to do it, that's a really big class. But it begins to address the scale at which these things are beginning to operate now. And the materials that we're getting in are of very high quality. The schools that offer our curriculum offer it at a variety of levels. So some schools that are science, technology, engineering, and mathematics academies offer this as early as the 9th grade. Other high schools offer it really as a capstone senior year course. But most of our schools have said the students are so engaged by this, they want a 2nd year course. And so we're trying to address 2 problems in developing a 2nd year course. One is, how do we build on what they've already learned and give them an additional educational experience? But then how also can we begin to think about giving them credit that they might actually be able to use at a university? Right? So I mentioned we're offering a dual enrollment option at UT Austin. They'll take a 3-unit engineering course. They'll get 3 units of engineering credit. If those students were to come to UT Austin, we'll say, that's great. It counts to your GPA, but doesn't count to any graduation requirements. We want to change that. We'd like to have some of these courses have the potential to allow students to place out of various courses. And if you look around the engineering curriculum and say what's commonly taught, it's very often computing. So our chemical engineering program has a basic computing class. Most ME programs do, most bio programs do, and so on. So we're experimenting with doing this, and we're going to be we're piloting this year in a small numbers of schools. And then we're continuing to expand our research on student impacts, effective recruitment strategies. We're also partnering with other universities. So I'll just particularly point out the partnership with Cornell. So Julie, do you want to raise your hand? Julie is going to be launching in 2017 with the Empire State Development Fund support that she's successfully obtained a program where 15 students from schools within a 30-mile radius of the Cornell campus will do their senior year on the Cornell campus, and Engineer Your World will be included in this senior year curriculum here at Cornell. So, final topic that I want to go over and then leave some time for questions is these general topics that I think are sort of unanswered at the moment, but strike me as really important issues for our profession. And so let me walk you through each of these. The first of them addresses the issue that's emerging in high school engineering education, that there are basically emerging 2 tracks in high school engineering education. One track is this track that I've been describing to you this afternoon. So the equivalent of a science course aimed at students who might envision themselves doing a BS in engineering. Another track, though, is for students who might see themselves completing an associate's degree in engineering or engineering and technology. Those are distinctly different preparations and 2 very different tracks. And collectively, both are extremely valuable, and we need to think about how those 2 interact as we go forward. Next thing is we're experimenting with this dual enrollment activity, but how do we really do this on a national scale? I know I'm scared to death of just 180 schools. There's 1,600 high schools in Texas. We have to think hard about how we're going to do this at scale going forward. And then, do those credits count for anything? Right now, the answer is no, not for an engineering degree. They may count towards other degrees, perhaps, as a science credit, but not towards an engineering degree. How can we deal with that? The College Board has been talking about, for a decade, an AP program in engineering. Right? If that happens, it's been a long decade, and it's still not apparently imminent. What should it look like? Should it be a test like the AP in chemistry or the AP in physics? Or should it be a portfolio like in fine arts? And the momentum for the last decade has been towards a portfolio. We'll see. Another question broadly I brought up earlier, which is now that we have high school teachers regularly teaching engineering, what is our responsibility as engineering educators if we have a school of education on our campus? What's our responsibility as educators in engineering to provide opportunities to train those pre-service and in-service teachers. And then how, as an engineering community, do we coordinate all these efforts? 8 years ago, I had no idea all this was going on. And I would say many of my engineering faculty colleagues are equally unaware as I was 8 years ago of all this stuff happening in high schools, but it's clear we need some sort of coordinated response to this. So these are challenging questions. And so here are the topics I've gone through. And if you want more information about the course, just go to engineeryourworld.org. And I'm going to leave these questions up if you need a prompt for more questions. But at this point, I'd like to try and handle whatever questions you have. So thanks for your attention.
Thank you, David. Yes.
How did you get your first 7 teachers? What did they come with?
So our first 7 teachers, well, I need to go back a step. So let me give you the evolution, the very early evolution. We discovered what was going on in engineering education, and initially we weren't quite as ambitious as I outlined here, and we just said, we'll just worry about teacher preparation. We do professional education, we do that well, we know what that is. We don't write curricula, all right? That was our attitude going in. And so what we originally proposed was just that we would create a graduate education program that would give teachers who are already teaching science or math a graduate degree that would allow them to specialize in engineering education. We had a first class of that group, a first group of master's students that began a 3-year process. And this was all with support from the National Science Foundation. The grant was $12.5 million. With a grant of that size, NSF comes and visits you. And as I'm sure Professor Archer can tell you, often they'll come and visit you and completely change your direction. And that's what they did to us. They said, how can you possibly train teachers if you don't know what curriculum they're delivering? If you don't know what the content is that they're trying to deliver? You'd better develop your own curriculum. So we already had this group of master teachers, largely drawn from the local, and we picked 7 of them from the local area, that we would use to help both develop the curriculum. So it wasn't a bunch of engineering faculty sitting in an office developing the curriculum. It was curriculum developers, active high school teachers, engineering faculty, a whole team with different expertise. And we already had a group that we were actively working with that we knew really well. And they tested our initial versions out in their school. So that's how we identified them initially. The next group we found because we had this NASA engineer who came in, and colleges around the United States have NASA-funded outreach programs that are tied to schools, and she linked us into those schools with their affiliates, and that's how we got our first schools distributed around the country. So we started with very targeted schools and very targeted teachers.
Yes,
What's the cost of the curriculum? And how does it compare? I'm repeating your question because I was told to repeat questions. So it appears on the video. So what's the cost of the curriculum and how does it compare to other costs? So I direct a center at the University of Texas at Austin. The associate director of my center, a fellow named Vince Torres, is the head of, served 12 years as head of the school board at the Austin Independent School District and had a lot of knowledge about what price points would be for schools. And so we established 2 types of costs for the cost of the curriculum. One cost was an ongoing licensing fee. If we're going to be able to continue to support teachers all the time, continually into the future, if we're going to be around forever without NSF grants, we need a regular licensing fee. That licensing fee is $3,000 per year per school. If we reach that price point by thinking about, well, what's an ongoing textbook cost for a course like physics? And what are likely science budgets for schools? Did a bunch of market surveys and landed at an amount of $3,000 per year, balancing what would be possible for schools and what would be a viable number so that we could get a critical mass of schools to support ourselves in the long run. So $3,000. There's also a startup cost. Two components to the startup costs. Component one is you've got to equip a classroom. One of the toughest design constraints in pulling together the curriculum was a self-imposed limit that we placed on ourselves of no more than $4,000 in equipment costs for the entire year and for the entire class. So you're doing this with groups, typically 25 or so in a class, 6 experimental stations in a class, 6 experiments, $4,000. That's really tough. What's particularly tough, and we went through multiple iterations on this, is you start getting inexpensive lab equipment and reproducibility just isn't there. We had a wind turbine experiment for a while, and we could never get it to produce reproducible results. And so, in any case, $4,000 there. And then the final cost is teachers got to come for professional development. Our costs, as we budget them, are about $2,000 per teacher, but the district's costs are our costs plus any stipend that they would pay to the teacher, plus if they've got to come to Austin to get that training, the living costs. Now, we've been fortunate to have NSF support. We also just recently got the University of Texas system to commit to support going forward, to support Texas high schools doing this. And so far we've been able to provide all the one-time costs for the schools so that the only cost we charge them is $3,000 going forward. And that's an annual cost. And we want them to pay that because we want to make sure that they won't get scared away if they suddenly have to pay something that they haven't had to pay for in the past. So nominally then $3,000 per year. Now there are perhaps 3 national curricula out there for high school engineering. One is a program called Project Lead the Way. And that's a program that is, I would characterize it as leading to and preparing students for an associate's degree. They're very non-communicative about their overall costs, but I've heard costs for those programs being on the order of $100,000 per school. It's an expensive program and requires a lot of what winds up being very expensive teacher training. But they don't publish their numbers, so that's just anecdotal. And the other is a very, very small program that just focuses on digital signal processing. And it was developed jointly between one university and Texas Instruments, and they're in a very small number of schools, and their costs are about the same as ours. So those are what costs are.
I have a question. So I'm from India.
Yes?
If we want to take something like this initiative to India, is that possible for this?
So one of the things that we're trying to work out now would lead to an answer of yes for that. Could you take this to India? Let me tell you the problem that we're trying to work out right now. So my goal would be universal access for students. If you're really interested in engineering, you want to have a high school engineering course there, and being from the University of Texas, if you're in Texas and you're doing that, I want you to be able to take our course. But what if your school doesn't sign up? Then you need some mechanism, like the mechanism that Julie is piloting here, right? Where a student could come in from a high school, maybe not do their entire senior year, but could come into a University of Texas system school near their home in Texas, do, together with other students who want to get a similar sort of thing, those hands-on activities, do that at a remote location, and then do everything else electronically. That coupling of hands-on activity and electronic delivery is a problem that a lot of people are working on to try and deliver education. And we're going to follow the developments in that, but we'd very much like to find ways to do that, but still retain the hands-on component.
No, if I was a school in Mumbai wanting to do that, or a school in India wanting to do that, then no problem.
No problem.
So we just follow the same thing you're saying, send people here for the training,
Sure.
pay you the license fees and all
Sure,
that.
right.
Okay, all right.
Right.
So I know you gave a quick overview of the projects, but they seem very Edisonian. Guess.
Oh,
go off
yeah,
and test
right.
on that. Is there any mathematical analysis? Is there anything quantitative?
Yes, absolutely.
Right, good.
So we had an advisory board throughout this process. So Mike's question, basically Professor Duncan's question, was essentially, we want to, you said it very nicely, we want to avoid being Edisonian, which means guess this, guess that, really put in the analytics so that you make informed design iterations. And every design project was, every one of those major modules was designed so that there would be detailed analysis that needs to be done at each iteration step, at each design step. Now, we're limited to algebra, all right? So we can still do mass and energy balances. We can still do lots of great things. But we don't do, another way of characterizing this is gadgeteering, all right? And so every design project has by necessity either programming and logical thinking or mathematical analysis in the design.
Okay.
So you referred to this curriculum as to a startup, basically. So my question is, do you expect to have any profit from this later on, or is it just
So one of the elements that I think leads to success here is our branding of this with the University of Texas. And it could equally well have been successful branded as Cornell or branded as any other top-tier institution. What gives it credibility is that linkage with a top-tier engineering school. That's what will give people confidence that, yes, this is a rigorous engineering experience. And if we lose that, I think we lose a large part of our advantage. Having said that, any university administrators in the audience, one of the things I worry about is the income stream. So we've priced our curriculum based on what it will take us to continue to support our activities. Now, if somebody starts taking 60% indirect costs off the top, all the costs go up and suddenly things get more expensive, and maybe we'd be better off operating as a nonprofit or in some other mechanism. I hope not. And so I hope we can continue to operate within the context of a College of Engineering, because I do think it's so important for the future of the profession, and I think the linkage with university level instruction is so important.
So, Jade, I'm going to get you next, but I want to ask one question. You keep referring to we and us. Who are we and who is us?
So
Who actually does this at University of Texas besides you?
there are two engineering faculty, myself and a mechanical engineer. You may know him, Rich Crawford.
Okay. Yeah, I know Rich.
And we're the two engineering faculty who've been involved with it from the outset. We also have some College of Education faculty who primarily do the research.
Okay.
Okay? So we have one department or College of Education researcher who's primarily interested in how are students learning as they're operating in these small groups. what's the level of argumentation that goes on as the design teams are making their decisions? And so she goes in and observes the classrooms and tries to figure out how can we make that experience and guide that experience to make it more effective. We have another researcher who's looking at the large numbers that we're now getting and thinking about what the diversity of
So
the...
it's a handful of faculty? Is there a staff or
So
administrators? Or
we've had 4 permanent research staff for the last several years. We just recently got support from the University of Texas system that for the next year and a half or so is going to allow us to expand that to about 10.
Oh, wow.
And so it will include somebody who can go out and help us do the marketing to schools. It will include,
It's kind of like eCornell or something.
yeah, so about that many people.
We'll take 2 more. Jade, you're next.
So, I'm kind of going off the Soraya's question, so it's like here. I appreciate that there seems to be underrepresented minority recruitment, so women, blacks, Hispanics. But my concern here is that charging a school for their education will kind of crowd out what I consider a bigger underrepresented minority, so that is the low-income rural students, unmarried children. So, what are you guys doing about that, if anything, at this point? Because I know this is kind of in its infancy, and what do you plan on doing about it, especially after NSF funding runs out, if it runs out?
Right. So we're particularly concerned about our ability to attract schools if we can no longer take care of those startup costs for them. For schools in Texas, we have support from the state of Texas through the University of Texas system to continue doing that for the next year and a half and maybe beyond. So one thing that will happen is we'll focus a lot more recruitment in Texas. But in the longer term, I think that that's a serious issue that we need to deal with. As we've been not talking about this program a whole lot until the last 6 months or so. And so I'm going to give you what I perceived over the last 6 months, although the evidence is still quite limited on this. And as we've begun presenting this to industry sponsors of the Cockrell School of Engineering, to individuals who are loyal alumni of the College of Engineering at the University of Texas, there's been tremendous interest in this, and at a level where individuals can, or foundations or other organizations can support particular schools and enable them to offer the curriculum, there's the most resonance. So we're going to be doing a lot of fundraising to get to a model that is not unlike the tuition model at colleges, where you say the price is X, but gee, we have all these scholarships if your school has need and it's unable for you to afford what the true price is for us to deliver the education.
So David, so you started and mentioned the word outcomes, and I'm curious to know what sort of outcomes are important to you, and what do they tell you thus far?
The outcome to me that's important is that we attract great students to engineering in the United States. That's the outcome that got me engaged. That to me remains the central outcome. I'm very proud to be an engineer, a Cornell engineer, and the profession has been wonderful to me. And I think it can be a wonderful career path for a great many people. We want to be able to do 2 things by exposing students to this in high school. Number one is perhaps giving students who may not have ever thought about engineering because they never knew someone who was an engineer, a good representation of what it is that engineers do. And then we want that experience to be accurate enough for those who, at the end of the day, decide engineering is for me, great, they've got a good foundation. But if they decide engineering is not for me, they haven't wasted a year of college tuition pursuing a curriculum that now they're going to shift out of. Allow them to make better decisions. So it's not to make everybody into an engineer, it's to give everybody an exposure to what the profession is, allow them to make accurate judgments. And so we're going to track students as we go forward. You saw our numbers were pretty small initially. We're just now getting to the point where the numbers are really big enough that we can do some long-term studies about how many of them are matriculating into engineering programs, how does their outcome fare relative to students who didn't have these experiences, and so on. So those are additional numbers that we'd like to track.
Okay, very much. That was really interesting.
Thanks.